Hello and good afternoon. This is Craig Kozminski with experiment number eight's pre-lab video. In this experiment, we will be looking at the reaction of a metal, specifically magnesium, when it is combusted in air. Before getting into the details of this experiment, I want to make a note on the content of this week's lab. This being the week of March 18th, you will have an in-person quiz, and this quiz will consist of information from not experiment number 7, but experiment number 6, which was our electrical energy lab from about a month ago. The last time that you came to lab, we would have gone through experiment number 6, looking at the conversion of electrical energy into mechanical energy. That was the process of lifting the weighted pan off the floor using the motor, as well as converting electrical energy into heat energy using our heating element, which was submerged in water inside of our calorimeter. So to prepare for tomorrow's in-person quiz, please make sure you go back and review experiment number 6. Now you might be thinking, well, Mr. Kozminski, if this is experiment number 8, what happened to experiment number 7? Well, if you take a close look at your syllabus, you'll see that tomorrow you will be asked to turn in pages 71 through 72, which are from the previous experiment, experiment number 7, as well as pages 79 and 80. And so because of our extended break, we did have to cut experiment number 7 from the lab. However, we do want you to focus on completing these two pages, pages 71 and 72. So, as a quick review of what you've likely already covered in lecture by this point of atomic structure, we can, using the periodic table, determine the number of subatomic particles in a isotope given the following information: the mass number and the symbol. And so, if we were, for example, to take a look at sodium, whose elemental symbol is Na, then we would look to the periodic table to find sodium. Now, using your periodic tables, there should be one printed in the back of your lecture manual, not your lab manual. That periodic table is incomplete. But the atomic number for sodium is 11. So 11. To determine the number of protons, that's going to be equal to the atomic number. So, because I have 11 as my atomic number, that's also the number of protons. Now, the next piece of information that's important is that we are being told that this is a neutral atom. If you recall that protons contribute the positive nature or the positive charge to the atom, then you should also recall that electrons contribute the negative charge to the atom. And if the atom is in fact neutral, the assumption that we can make when an atom is neutral is that the number of protons will be equal to the number of electrons. So if I have 11 protons, then I will also have 11 electrons. To determine the number of neutrons, this is going to be equal to our mass number minus our atomic number. Another way of saying this is that the mass number is equal to the sum of the protons and the neutrons. So for sodium, because we are told that the mass number is 23, and we determine that the atomic number from the periodic table is 11, then we know that the number of neutrons in this neutral sodium atom is going to be equal to 12. Now, just a word of caution, your mass number is always going to be a whole number. So when you look to the periodic table, you will not find the mass number there on the periodic table. You'll find a slightly different value, which is called the atomic mass or the average atomic weight. And that number oftentimes ends in a decimal. You are not to use this number on this worksheet, page 71. Now in part B, the atomic structure, we're asking you to determine the overall total number of electrons in an atom and to fill the shells according to the pattern of 2, 8, 8, and 18. And so if we were to find the symbol for hydrogen on our periodic table, we would say that hydrogen has the symbol H, and it has a total of 1 electron equal to its atomic number. Its 1 electron is going to go into the n equals 1 shell, And then we will have 0 electrons in our second, third, and fourth shells. So using this pattern, please complete pages 71 and 72. Now, this brings us to experiment number 8, reactions of metal in air. And hopefully at this point, you've already gone ahead and read the entire setup for this experiment. If you've not done so yet, I would encourage you to pause the video and do so at this time. In this week's experiment, we are going to be looking at a combination of magnesium with 2 different gases that are found in air. The first gas that we will see magnesium interacting with is the most common gas in our atmosphere, which is nitrogen gas. When magnesium forms or interacts with nitrogen gas, it'll form magnesium nitride. Now, we'll also see that magnesium will interact with oxygen gas to form magnesium oxide. And if we were to look at our overall goal of this experiment, you might say that the overall goal is to determine the empirical formula of magnesium oxide. So the second part of this experiment is after we've combusted the magnesium in the presence of air, which has a lot of nitrogen, is to purify our impure product. And another way of thinking about this is we are going to aim to convert our undesired product, our magnesium nitride, into the desired product, which is magnesium oxide. So in this second part, the purification part of the experiment, we are going to wash our impure product with water. This is going to cause a chemical reaction to convert the magnesium nitride into magnesium hydroxide and ammonia gas. Now, magnesium hydroxide, when heated, will undergo a decomposition reaction to form our magnesium oxide and our water. We will drive this water in the liquid phase off by converting it into a gas using a constant supply of heat energy. So, in summary, and this screen will be available to us during the lab tomorrow, we're going to burn magnesium in air. And when we do this, it's going to make our desired product, magnesium oxide, and our undesired product, magnesium nitride. We will then purify the impure product, by adding water and eventually heat. And at the end of this reaction, we should have in our crucibles only our magnesium oxide. Now, there are some safety concerns for this experiment, so I would encourage you to pay careful attention to any bolded text, as well as the fine details of our procedure. For example, here in step 14b, we want to make sure that we do not heat our impure product, to which we have just added water, too violently. If we superheat that solution, we could cause some of the product to splatter out of our crucible, not only ruining our results, but also potentially causing problems as to contamination or even getting some of that product on yourself, which we want to avoid at all costs. Finally, I hope you've read the lab report questions. That it's important to helping you understand what we're going to be doing in lab tomorrow. But I want to take a quick look at our exercise worksheet, pages 79. So on page 79, there are 3 examples of determining the simplest formulas for the given compounds. And the form that we're going to be using for this is to take a look at the mass to mole conversion using the molecular weight of the substance, or the atomic mass, to divide each by the smallest number of moles, and then finally multiplying if necessary to achieve whole number ratios. So if we were to look at our first example problem, it says a compound sometimes used in fireworks to produce brilliant red colors is strontium chloride, where strontium has the symbol of Sr and chlorine has the symbol of Cl. It says we have a 8-gram sample, which contains 4.42 grams of strontium and 3.58 grams of chlorine. Find the simplest formula. So our first step is going to be to convert 4.42 grams of strontium, oh, forgive me, let me make that a lowercase r, into moles of strontium. The way that we're going to do this is we're going to find the atomic mass of strontium on the periodic table. And we're also going to do this for 3.58 grams of chlorine. We're going to divide it by its atomic mass on the periodic table. And this is going to give us some number of moles of strontium and some number of moles of chloride. Next, what we are going to do is we're going to divide both of these numbers by the smaller of the two. So whichever number is smaller, either the moles of strontium or the moles of chloride, we will divide by the smaller value. And when we do this, this is going to give us a number of strontiums and chloride atoms in the formula. And from this, if those numbers are near whole numbers, that is having decimals that end in approximately zero point 0.9 or 0.001, then that's going to be a good sign that this is our simplest formula. And if it's not, then we will have to multiply by a coefficient. And I'm confident that you've already gone ahead and done some of these types of problems in the lecture. So it would be in your greatest benefit ahead of tomorrow's lab to make sure that you review the information from experiment number 6, on which your in-person quiz will be on. It will be in your best benefit to attempt pages 71 and 72 from experiment number 7. Yes, we did not conduct experiment number 7, but the exercise worksheet we are asking you to submit to us as a part of your in-person work tomorrow. Attempt, page 79, those 3 empirical formula questions. And as always, read carefully over the experimental procedure for experiment number 8, reactions of a metal in air. Thank you for watching this video. I hope it's been helpful to you, and I look forward to seeing you all in lab this week, as does your lab instructor.